All right, I wanted to take a quick look at this car going around a flat turn situation. So we're on an unbanked road. The road's level, it's horizontal, and this car is going around in a circle. And so we're trying to think about the forces involved here. The car is on a flat road. You've got gravitational force down. That would be mass times G, the 10 newtons per kilogram. Got a smoosh poosh pointing up, and if we don't have any kind of added downforce from wings like on an F1 car or an Indy car, that smoosh poosh is going to equal the gravitational force. And what's causing it to turn? If you think about the bowling ball lab, we used a rubber mallet and we were smacking the ball and hitting it in a direction towards the center of the turn to make it go around a corner. What's acting like the mallet here? So if you pop over here, I found this little video on the YouTube. Kind of listen there. And you can hear the tires squealing. At least I hope you can hear that on the video. Tires squealing. So the tires are sliding across the ground. That should give you some understanding of friction being involved in this. If you're going too fast around the corner, the tires will squeal. Maybe you've had that experience on that I-8380 interchange if you've gone a little too quickly trying to get up to speed. So there's a frictional interaction, and that's going to be, oh my goodness, that's going to be pointing towards the center of the turn. Okay, so if I've got the center over here, there's friction acting here. And I want to go as fast as I can without sliding. So what I'm talking about here is static friction, FFS. Okay. That's, again, if you kind of think back to when we talked about friction, that's the maximum force I can get. If the tire starts sliding, then I'm subject to kinetic friction. That's not as much force. So that's going to kind of affect things here. So I threw some numbers on here. I give you mass of the car, radius of the circle, assume standard conditions for rubber tires on a concrete road. All that means is if it's dry concrete, it's not raining, then we're talking about a mu s of 1.0. In other words, the static frictional force equals the smoosh poosh. So our equations that came out of the lab, depending on which version of the lab you did, unbalanced central force equals mv squared over r. That's the tangential velocity squared over r. Or mass times the radius times omega squared. Okay. If you think about how you get back and forth between v tan and omega, you'll see those things are equivalent. And if you look at it, it's not that dissimilar to our old friend FUMA, okay, except that we've got this subscript C thing going on here because we're talking about a center-directed or a center-seeking acceleration. If you didn't get a chance yet, check out pages 96 to 97. And if we just pull this out of the equation, that centripetal acceleration, v tan squared over r or r omega squared, if you check those out dimensionally, you'll see they're equivalent in terms of units as meters per second squared. And that's actually how I caught myself when I screwed this up a little bit ago. But if we just work through the problem here, we're saying that the frictional force is equal to the unbalanced central force. If you look at this diagram here, if I go smoosh poosh up and I go friction over and then gravity down, then here's my unbalanced force pointing towards the center, and it's the same as that static frictional force. Okay, so they're equivalent. So I can say mu FSP equals m v tan squared over r. And again, the smoosh poosh, because we're on a flat road and we're not considering any kind of downforce, the smoosh poosh is equal to the gravitational force. So I can just write this as mu mg equals m v tan squared over r. And hey, what do you notice? M drops out here. Mu g equals v tan squared over r. And then we can get that the speed with which it can go around the corner is going to be equal to mu G, R. So it's going to depend on how tight the corner is and the conditions, the coefficient of static friction, and then obviously the gravitational constant. The mass dropped out. Doesn't matter if I'm dealing with a Fiat or a dump truck here. So mu is 1. G is 10 for all intents and purposes. And then R is, the radius is the 30 meters. So this is effectively meters per second squared. So that's going to give everything under the radical there, meters squared per second squared units. And it's going to have the units of meters per second when I'm done. That was the check that helped me catch that I screwed it up. So we're looking at the square root of 300-ish. Let's see, calculator. Boop. So 17-ish meters per second. And again, miles per hour, take that times 2.25. And we're talking about somewhere in the ballpark of 40 miles per hour. So this vehicle could maintain a speed of 40 miles per hour while turning on that radius and still make this turn without sliding. So in inspecting the equation, you see if we make mu bigger, obviously that's going to help out here. So if you were somehow able to get a higher coefficient of friction, that would help out. Or if I make R bigger, that could help out here as well. And so the way that that's achieved, if you think about people driving down, Camp Cardinal Road is kind of bendy like this. And those people from like Powesheik County or whatever, when they go driving down that road, they kind of take a path that just follows the curves exactly as they maintain a maddeningly low speed of 20 miles an hour going through there. But the locals know what the NASCAR folks refer to as straightening the curves. If you look at the radius of curvature here for this, if you think of this as a circle, maybe I'll use a different color. If you think of this as a circle right here, oh yeah, that's a great circle. Okay. Or even right here, if you see this circle, circle. We want to make a bigger circle, so to say, with our turn. So when I'm coming through this one, maybe if I start a little wider in the lane and then try to hit a little bit closer to the apex of the turn, and then I come over here and do a similar thing. Now I've straightened the curves, as the song used to say. Basically what I've done is I've made the radius of the turn bigger. Okay, so there's a bigger, that's a terrible attempt at drawing the radius. That's a bigger R there. And if you look at the turn over here, this is a really big circle. And so I've made the radius of the turn bigger. That allows you to maintain a higher speed as you go through the corner. A little closer to that posted speed limit of 35 on Camp Cardinal. All right, so that's a little bit about turning on flat corners.